Okay, hello guys. I don't think anyone, I don't think anyone else is gonna join, so we're just gonna start now. So today we're gonna be talking about orders. That's very cool. So this is just very quickly what we're gonna be doing today. First, we're gonna be actually no, you guys can just read this. It's not that important. Okay. So so before we can do anything of orders, we have to first understand what the order actually is. So um the order of an element is is like mod p. It's the smallest power of it, which is 1 mod p. So for example, if you have the number 2, 2 to the power of, like, if you consider 2 mod 7, 2 um to the power of 1 is 2. Oh wait, no, that's the example. Okay, wait. I'll just quickly go over the example so it makes a bit more sense what the order is. So I'll just share my screen. Hold on. Okay, I hope you guys can all see my screen. Um, okay, so oh wait, it is um so we're gonna consider the powers of 2 mod 7. So 2 to the 1 is equal to just 2 mod 7, and then 2 to the 2 is equal to 4, which is 4 mod 7. 2 to the 3 is equal to 8, which is 1 mod 7. So hold on. So the smallest power of 2, which is 1 mod 7, is 3. And then I'm gonna do a different example. So let's say we wanted to find the order of um 4 taken mod 5. So 4 to the 1 is congruent to 4 mod 5, and then 4 to the power of 2 is 16, and then this is like 15 plus 1. So this is 1 mod 5. So then the order of 4 mod 5 would be 2, because 4 to the 2 is the smallest power of 4, which is congruent to 1 mod 5. Um, and then quick note. Oh, wait. Oh, quick note. Remember by Fermat's little theorem that p minus 1 is congruent to 1 is congruent to 1 mod p, but like the order of the order like isn't always p minus 1. Sometimes it's smaller than p minus 1. So just keep that in mind. Okay, so here's some basic properties of the order. The first one, okay, so I read somewhere they said that this was called the fundamental theorem of orders, but like I don't know why it's called that. Yep, that's just a fun fact. So if a to some power is congruent to 1 mod p, then that power is divisible by the order. And then I'm gonna quickly prove this because it's pretty easy to prove. Okay. Um. So let's say that a to the n was congruent to 1 mod p, and then we're gonna assume that the order of n does not divide n. So this means that we can write n as in the form like an plus k, where k is like where k is smaller than n and k is not equal to 0. I think this is like Euclidean division or something. Yeah, so you can do this. And then we know that, oh wait, hold on, this should be, yes, thank you. It should be, I'm just gonna call it, what should I call, I'm gonna call it this x. I'm gonna call the order x. And this should be this. So then we know that ax is congruent to 1 mod p, and also because like x is the order, and this is just by definition, then also a to the, oh wait, I should not call that a. Okay, I'll call that b. A to the bx plus k is also equal to 1 mod p. So then if we divide, so from this, if we took both sides of the power of b, we get a to the bx is equal to 1 mod p. So if we divided a to the bx plus k by a to the bx, this would be congruent to 1, and then this would also be equal to a to the x mod p. So a to the x is equal to 1 mod p, but then this is a contradiction because we have a to the power of k is congruent to 1 mod p, but k is smaller than the order, and that's not possible because we defined the order to be the smallest power, where a to the power of it was congruent to 1. So that means that this assumption here was not true, and this means that the order will always like any power of a that's congruent to 1, the power is always divisible by the order. And then the second property says that if you have a to the n is congruent to 1 mod p, and a to the m was congruent to 1 mod p, then their greatest I wrote the nm like thing, it just means the greatest common divisor. So the power a to the power of the greatest common divisor of n and m is also congruent to 1 mod p. And the proof for this is pretty simple. I think Hao-Tian can prove it if he wants to.
Yep, hello. It is simple to prove, and I will prove it for everyone. So I forgot the problem.
Oh, it's if a to the n is congruent to 1 mod p,
Mm-hmm.
and a to the m is congruent to 1 mod p.
Oh,
And
okay. So we are asked to prove.
wait, fun fact, this is actually, some people call this the GCD trick. So that's pretty cool. If you like wanted to use this, you could just say by the GCD trick. Or like you could also not say that because like I think most people know it. But
Oh,
yeah.
okay. So we know a. Oh no. We know a to the n is congruent to 1 mod p. Then by the first property, we know order of a divides n. And then similarly, we know this. So order of A also divides M. So then order of A divides the greatest common divisor of N and M because it divides both of them. So then A to the greatest common divisor of N and M is also congruent to 1 mod P because that's by the definition of order, right? Because if the CD is equal to Q times order, then that is A to the power of Q times order, which is 1 to the power of Q, which is 1. Wow. Okay, thank you very much for asking me to prove that. That was lots of fun.
Okay, so here's our first problem. I'll give you guys a bit of time to try this problem. Wait, Houghton, how much time do you think we should give them for this problem?
Um, I think 5 minutes. Actually 4 minutes.
Okay. You guys get 4 minutes to try this problem.
Oh, wait, as a hint, um, 2 to the P minus 1, I mean 2 to the P is congruent to 1 mod Q. So therefore, by property 1, we actually know the order of 2 divides P. Mm. Okay, so now I will present the solution. But actually, I don't know how to solve the problem because it's really tricky. So could someone please give me some hints? Okay, I don't think I'm getting any hints, so I'll solve it now because I thought of the solution after no one gave me hints. Anyways, um, q divides 2 to the p minus 1, which is the same as 2 to the which is the same as 2 to the p congruent to 1 mod q. And then by property 1, which as a reminder, there was if a to the n is congruent to 1, then order of a divides n. Now we know the order of 2 divides p, but p is a prime, so that's very cool actually. That means order 2 equal to 1 for p, because the only two factors of p are these two numbers. So if the 2 is equal to 1, then we know 2 to the 1 is congruent to 1 mod p, which means p divides 1. But that is a contradiction. That doesn't make sense. So otherwise, order of 2 is equal to p. But then that means... Okay, so by Fermat's little theorem, we know 2 to the q minus 1 is congruent to 1 mod q. So that means order of 2 has to divide q minus 1. And that's p. P divides q minus 1. So q minus 1 is at least p, which implies q is bigger than p. Wow. Okay. Any questions? By the way, the next problem I really will not be able to solve. So like, please work very hard and give me lots of very good hints, you know? Okay, could you please read out the problem for everyone?
Okay, so I'll read the question out in case you guys like are unable to read. So it says, prove that for an odd prime p, if p divides two n squared plus 1, and then I haven't said this, but n is like it's an integer, in case you guys thought it was a real number. So if p divides n squared plus 1, then p is congruent to 1 mod 4. So that's what you guys have to prove. I think you guys probably get another 4 minutes to just try this problem.
Mm. So the hint for this problem is n squared is congruent to -1 mod p. And -1 is basically 1, you know? So how do we use an order? How do we use orders in this problem? Okay. Firstly, can anyone give me some hints, please? Guys, I actually forgot what order means just now. Can someone please give me a hint to what order means? Okay, never mind then. I remember what orders is. Um, so n squared is congruent to n. P divides n squared plus 1, which means n squared is congruent to -1 mod p. But when we look at the definition of order, it's what a to the order is congruent to 1, but this is -1, so that's quite problematic. So how do we deal with this problem? If we square -1, that becomes 1. So n to the 4th is congruent to 1 mod p. And then now I just want to point out a cool fact that we used in the last problem as well, which is order divides p minus 1. Because by Fermat's little theorem, say order of n, we know n to the p minus 1 is congruent to 1 mod p. And by property 1, we know order divides p minus 1 because n to the p minus 1 was congruent to 1. So that's a cool fact. So then, yeah. Now if we go back to the problem and we use property 1 again, we know order, what? We know order of n divides 4. So order of n equals 1, 2, or 4. And it can't be any of these, right? Because otherwise this would not have happened. Oh, actually, um, wait, am I sharing my Oh, sorry, I realized I was not sharing my. I'm very sorry about that. Okay, I will commentate over my working. So this was the problem in the condition and the problem. And if we convert that into mods, that's that, right? And then we we want to try use orders because this tutorial is about orders. But when the orders are used, it's congruent to 1. And this is -1. So we want to make it into 1 by squaring it. And now we get this. And then this was the cool fact I talked about. The order of a number always divides p minus 1 because any number to p minus 1 is congruent to 1 mod p. And by property 1 stated in this tutorial, the order always divides. If m to the something is congruent to 1, then order divides that something. Okay, so back to the problem. By property 1, order of n divides 4 because n to the 4 is congruent to 1, which means order is 1, 2, or 4. But then, for example, order equals 2, then n to the 2 should be congruent to 1. But we know n to the 2 is congruent to -1, which does not make sense. Yeah, because if it's also congruent to -1, then that means p divides 1 minus -1 is equal to 2. And this is where you use the fact that p is an odd prime. Or I lost my working. Oh, okay. Um. So therefore, order equals 4. And then, yep, using our cool fact, we know 4 divides p minus 1, which is the same as p congruent to 1 mod 4. Wow. Okay. Does anyone have any questions? Or maybe they have a really cool solution that they found and they would like to present it, Okay, I think that's a no. Actually, maybe I should count down from 5. Um, you guys have 5 seconds to give me a cool solution. 5, 4, 3, 2, 1. Okay, there was no cool solution, unfortunately. Okay.
Okay, so now we're gonna move on to the idea of a primitive root. So what a primitive root is, it's an integer g. We can call it a primitive root mod p if when you take g to the power of 1 and then so on, the order of it is p minus 1. So what this means is that okay, so here on the slide it says that this means that the set contains p minus 1 distinct residues, which means that no two of the for 2 powers less than p, no 2 of g to the powers are the same. So I'll quickly share my screen and just prove this, and I think it will make a bit more sense when I do that. Okay, so by the way, for a prime number, there always exists a generator, so that's pretty cool. Oh, I know. Oh, it's the primitive root can also be called a generator, which is why we write g. So if I say generator, that's the same thing as a primitive root. So okay, so we have g, and then we know that the order of g is equal to p minus 1. Now let's say we had a and b between 1 and p minus 1, and then assume, for the sake of contradiction, that g of a was congruent to G of B. And then we'll log that A is solving B. So then what this means is that if we divide both sides by G of A, we get G of A over G of A is congruent to G of B over G of A mod P, which means G of B minus A is congruent to 1 mod P. But then because B is less than P minus 1, less than or equal to P minus 1, B minus A is less than the order of G. And so this contradicts the fact that the order is the smallest power that's congruent to 1 mod P. Which means that it's not possible for these two to be the same. So this means if you consider all the powers G1, G2 to all the way to G P minus 1, these are all different mod P. And because, like, if you consider mod P, like, obviously, none of these are 0 mod P. So it's just 1 to P minus 1 mod P. So, like, because there's only P minus 1 possible mods of P, and then each of these is a different model, of P, this set G1 to G P minus 1 is just the same as 1 to P minus 1. It's just that the order is like different when you do it like this. What this also means is that for every number A, which is co-prime to P, which means that it's not congruent to a 0 mod P, there exists some power K of the generator, which is congruent to A. So for all A, there exists K such that G to the K is congruent to A mod P. So that's why the generator is particularly useful, because you can write every number as a power of the generator. That's pretty cool.
Thank you. Yeah, so that's the primitive root. And now here's a problem using the primitive root or generator. So, yeah, I'll read it out for you guys. Let P be an odd prime and G is a generator mod P. Show that G to the P minus 1 over 2 is congruent to -1 mod P. And you guys have, 4 minutes to do this. Okay, hopefully that's enough time to make some progress. Or hidden by the wow. Oh, that was a secret. No, you do not see that image. I'm very sorry to the person involved in that image, but hopefully no one saw it. Um, okay. Anyways, here is the problem. Okay, so yeah. Um, Firstly, I'd like to go over a mistake. It's not wrong, but oh, but it's not completely correct either. And it's very reasonable to make this mistake because we know g to the p minus 1 over oh, okay, that's a bit ugly. Okay, I'll remove the brackets, hopefully. Oh, that's so bad. Okay, g to the p minus 1 over 2 is called negative 1 mod p. And the power p minus 1, that reminds us of Fermat, right? And we know this. And it's very easy to get from this to this by just squaring both sides, and that's very reasonable to think of. However, nothing you've done is wrong. This is completely correct. Everything in here is correct, but this doesn't prove the problem though, because for example, I could say claim 7 equals 8, and then my proof is 0 times 7 equals 0 times 8, multiple side by 0. And that gives us 0 equals 0, which is indeed true. That's similar, right? We have a claim that we're trying to prove, and then we did correct things to get to a correct conclusion, but that doesn't mean we can go backwards. We've worked forwards, but now we need to get back to the original claim. Okay, so anyways, first, to give you guys a better understanding of generators, I will give an example. So let's say P equals 13. So 2 is congruent to 2 mod 13. 2 to the 2 squared. Okay, let's make that 2 to the 1. 2 squared is congruent to 4. 2 cubed is congruent to 8. 2 is 4. Yep. And as expected, 2 to the 12 is congruent to 1 by Fermat's little theorem. And then if you look at the numbers, they are all different, right? We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 different numbers, and all 12 possible remainders, except 0, but obviously 0 is not coming in. And then also this acts as a good small example for the problem we're working on, which is g to the p minus 1 is congruent to negative 1. And indeed, that's true. 12 is congruent to negative 1 mod 13, because 12 is 13 minus 1. So, how do we do this? Actually, let's keep that example. Wait, just so you can compare with a more concrete example instead of g and p and stuff. So we look at g squared, g cubed, right, all the way up to g to the p minus 1. And this is a reordering of this. And we also know g to the p minus 1 is congruent to 1 mod p. by Fermat's little theorem. So, yeah, and now we can relate this to the problem. We know if we let g to the p minus 1 over 2 equal x or p, just to make it easier for me to write, then we know x squared is equal to g to the p minus 1 was congruent to g to the p minus 1, which is congruent to 1. Does this mean x has to be negative 1? So from this, we get p, what the heck? We get p divides x squared minus 1. And that is equal to x minus 1 times x plus 1. So now we know x is congruent to 1 or negative 1. But we're still not there, right? We want it to be negative 1, but that means we have to eliminate the possibility of 1. And now we use this fact a second time. That is, we know 1 already appears in this list. So therefore, g to the p minus 1 over 2 cannot be 1. Because, for many reasons, because firstly, 1's already taken, and we know all the numbers are different. But then also, that would mean order of g is at most p minus 1 over 2, which is against the definition of g, which is the order is p minus 1. So, yep. Yeah, that's it. Okay, here's the next problem. Oh, okay, yep. Here's the next any questions, by the way? Oh, and also if you have any hints for how to solve that last problem to give me, then I would greatly appreciate some hints. Anyways, now we move on to problem 4. This problem, it should remind you a lot of the last problem, no? Because we got congruent to negative 1. So yeah, this one you get 2 minutes to work on it. Okay, hopefully that's enough time to get some progress on this problem. So, oh, actually, something that you do need to know, which Jade did mention, every prime has a generator, right? Because you can't just assume that you can pull out G out of nowhere. For example, some numbers do not have generators. I, yeah, for example, if we consider mod 6, then first let's try 1. 1 to the 1 is 1. 1 to the 2 is 1. 1 to the 3, 1, and so on. So that obviously does not work. Now let's try 2. Um, and that obviously does not work. And if we try 3, that also does not work. If we try 4, that also does not work, and so on. I will stop going on with them. The point is, you can't always just pull out a generator. But if we're considering mod a prime, then it is proven that it is always a generator. So let G be a generator mod P. Then by the last problem, we know G to the P minus 1 over 2 is congruent to negative 1 mod P. But then we also know P minus 1 is a multiple of 4 by the condition. P is congruent to 1 mod 4. So then P minus 1 over 4 is as P minus 1 over 4 is an integer. Let's say it's equal to n. And now we know G to the n squared is congruent to G to the P minus 1 over 2, which is congruent to negative 1. So, yep, that's that. Okay, any questions? Okay, here is the next problem. Um, okay. Um, Okay, because this problem is quite challenging, I'll give you guys another minute and then I'll give you guys a hint. Okay, so here's a hint. Wait, actually, I'll move down the problem. Well, okay, so here's the hint. We are asked to find 1 to the n plus 2 to the n plus all the way up to p minus 1 to the n. And 1, 2, 3, all the way up to p minus 1. If we think about what we've been taught in the tutorial, it should remind you of something, and that is that these two sets, this set is equal to g squared, g cubed, all the way up to g to the t minus 1. So, yeah. And then also for another hint, the condition p is bigger than n plus 1 is quite weird. So ignore it for now, because it is a bit uncertain how you're meant to deal with it. Okay, and then also another hint, 1 plus 2 plus up to, wait, no, 1 plus a squared plus a cubed plus up to a to the n, that is equal to a to the n plus 1 minus 1 over a minus 1, which maybe you're more familiar with this being on this side. Um, Also, this is a geometric series, so if you know that, then you can also prove it. But, yep. Okay, so now I will present the solution. Let's say let G be a generator mod P. And now we know the expression in the problem. Oh, firstly, can I have hints, please? Does anyone have hints to give me for this problem? Okay, no one has any hints. I'm really sad now. The expression in the problem that is equal or that's congruent to G plus, oh no, G to the N plus G squared to the N plus G cubed to the N plus all the way up to G to the P minus 1 to the N. Actually to make it a bit easier to type up, let's replace G to the P minus 1, 1. So now instead of that, we get 1 to the N and P minus 2. And that's because of this. Alright. Oh, that's so sad. Okay, and that is equal to G. Okay, that's equal to G to the, that's 1 plus G to the N plus G to the N squared plus G to the N cubed plus all the way up to G to the N to the power of P minus 2. And now this is beginning to look like this thing, right? So that is equal to G to the N to the power of P minus 1 over G to the N minus 1. Or it's a bit hard to read. And then now we notice something cool. G to the N to the P minus 1 is congruent to 1 mod P. I mean, it's congruent to, oh yeah, it's congruent to 1. Or equivalently, that minus 1 is congruent to 0 mod P. Because G to the P minus 1 is congruent to 1. So G to the P minus 1 to the N is 1 to the N, which is 1. And now we're almost done. But we also, so we know P divides this, but that doesn't mean P divides this, because the P might have gotten divided out. Sorry, the P might have gotten divided out by the denominator. And yep, so now we gotta prove P does not divide this. And now we realize that's how we use the condition that P is bigger than N plus 1, because then that means N plus 1 is less than P. which is the same as n is less than p minus 1. So therefore g to the n is not congruent to 1 or p, because g to the p minus 1 is congruent to 1. And yep, so now we're done with the problem.
Okay, so now we're gonna move on to cyclotomic polynomials. And I guess this is like a pretty hard, like the cyclotomic polynomials are pretty tricky. So it's okay if you don't like if they're a bit tricky or like if you don't understand them. But like I thought they were really interesting. And then like sometimes they do come up. So I thought it would be good for you guys to learn about them. So on the slide, it gives you this definition of what this cyclotomic polynomial is. That's kind of confusing. So I'm gonna go and like explain it a bit more. So I'll just share my screen. Okay, so let me see. So this so this like for each integer n, there's some cyclotomic polynomial, which I'll denote like this. And then this is like some polynomial. And then the way it's defined is so that for each n, xn minus 1 is equal to the sum, the product of, for each divisor of n, the dth cyclotomic polynomial. So this is like a bit confusing, but there is a reason why it's like this. So, but like before we get to that, I'm just gonna show you guys like how we can find this cyclotomic polynomials. So for n equals 1, x 1 minus 1 is equal to I won't bother writing this because like, so it's just for each divisor of 1, and the only divisor of 1 is 1. So it's just of x. So that means we found that the first cyclotomic polynomial is just equal to x minus 1. And now if we do x equals 2, we have that x squared minus 1 is equal to, and then the divisor of 2 are 1 and 2 and 1. So it's 2 of x times 1 of x. And since we know that this is x minus 1, you might recognize that you can factorize an x minus 1 term out of this. And so if you cancel these, you get that the second cyclotomic polynomial is x plus 1. Then if you do, I'll just go up to n equals, I think I'll go up to 5. Okay, so x for n equals 3, x 3 minus 1 is equal to phi of 3, x, phi of 1x, and then you can factor out this. So divide out by both sides, and then the third cyclotomic polynomial is this. And now n equals 4, it gets different because 4 has 3 factors, which are 4, 3, and 1. So x4 minus 1 is equal to 4 of x, 2 of x, 1 of x, which is equal to x plus 1 from back up here, and x minus 1. And then notice that this gives us x squared minus 1, and then we can also whoops, hold on, what did I just do? Wait, what? Okay. So anyways, you can factor out x squared minus 1, x squared plus 1 out of this. So then divide out by this, then you get the fourth cyclotomic polynomial is x squared plus 1. And then we'll just do this one more time for n equals 5. Yeah. Alright. Just in case, wait, you guys are a bit confused. When I write this, it means when I write this, it means the nth cyclotomic polynomial. In case you guys are a bit confused, because up here I wrote something different, but then this is just kind of annoying to write. So yeah. So now we'll just do n equals 5 to the 5 minus 1 is equal to 5. Oh, this symbol is it's called phi, by the way. Usually when you write it, it's you'd write the capital phi, which looks like this. But I'm a bit lazy with my handwriting. Yeah. So and we can factor out x minus 1. You guys, I think you guys should know that it's equal to this. You can factor it out like this. And then this one's just equal to x minus 1. So you divide out by both sides. Equal to x4 plus x3 plus x squared plus x plus 1. So I'll just write down all the cyclotomic polynomials we found so far. So it's equal to x minus 1. 2 is equal to x plus 1. 3 is I think that's a weak part. Yeah, it is. And some of you guys might have noticed the pattern. So for the cyclotomic polynomial of 2, 3, and 5, they look like xn plus minus 1 plus xn minus 2 plus 1. And you might notice that 2, 3, and 5 are each primes. In the case where n is a prime, you just have xn minus 1 is equal to phi of, I'll just write p. So x1, x, and then you can factor this out as and so you see that the pth cyclic polynomial when p is a prime is looks like this. So that's pretty cool. And so now I'm going to talk about why cyclotomic polynomials are interesting. Given a if you have the cyclotomic polynomial n, and if you have this is congruent to 0 mod p, this means that the order of A is equal to exactly n. So what we see, obviously, I'll just give you guys a bit of a reason for why this is true. So when we have this is equal to x minus a. So x minus 1. So if x minus 1 is congruent to 0, then obviously x is congruent to 1, and the order of 1 is just 1. And then next, for x plus 1, it's equal to x plus 1. So if this is equal to 0, then x is equal to minus 1. And you see that x to the power of 1 is minus 1, and x to the power of 2 is equal to 1. So that means that the order of x is 2. Now, if you think about it, from the way we defined it, xn minus 1 is equal to the product of all the divisors. So if you wanted to find the nth cyclotomic polynomial, it would be is equal to xn minus, n on top. And then you're dividing by the cyclotomic polynomial of all the divisors of n. So like, all the divisors of n which are less than n. So if you look at the expression xn minus 1, if p divides this, or this is equal to 0 mod p, this means xn is equal to 1 mod p. This means that the order of n is the order of x divides n. So the order of x is one of the divisors of n. So then here what we're doing, basically we're on the bottom, we're dividing out all the numbers which are like have a on the bottom we're dividing out by all the divisors of n which aren't n. So we're just getting rid of them, and then what we're left with is just all the divisors is all the numbers whose orders is exactly n, because you've got rid of all the divisors. It's okay. Like, does that did that make sense to you guys? I think it's okay if you guys don't fully understand like exactly why this is true. But the key takeaway here is that if you have the cyclotomic polynomial, the nth cyclotomic polynomial, and you applied a to it, and this is and p divided this, then the order is equal to n. And then you might have noticed here that all of these polynomials have integer coefficients, and that's always true. And then you might notice that, and then like, if you consider the constant term, they're always like plus or minus 1. So another, I guess, important thing is that like all the coefficients of the cyclotomic polynomial, it's always like all the coefficients are either 1, minus 1, or 0 for like when it's not there, and the constants terms always plus or minus 1. You guys, I feel like, yeah, you guys, do you guys have any questions on this? Oh, okay, it doesn't seem like there are any questions. So yeah, so we'll move on. Okay, so this is Okay, as you can see from the slideshow, this is a very, well, in my opinion, I think it's a pretty hard question. Yeah. I guess a hint is that this pretty directly uses, well, like the properties that I just talked about, where if P divides like the cyclotomic polynomial of A, then the order of A is equal to n exactly. I think I will give you guys 8 minutes to think about this and ponder. It's okay if you guys can't solve this, but like it would be good if you guys could make like some progress. Yeah, like any progress is good. So yep. Oh wait, I realized that class is supposed to end at 8. So I guess I'll just go over the solution now. But there is one more question after this. So if you guys wanted to stay, it shouldn't be too long because it's just one question. Yeah, okay. I'll just go over the solution. Wait, hold on, my screen shares forward. Okay, all good, all good. So we want to so we want to prove that there's infinitely primes of the form for so let's pick some number n. So for some n, we're gonna prove that there's infinitely primes of the form a n plus. No, I'll do k n plus 1. Okay. So we know that if some prime divides p of the cyclotomic polynomial and the nth cyclotomic polynomial of A, then the order of A is equal to n. And remembering the trick that Haotian talked about, the order of A divides p minus 1. So what that means is that n divides p minus 1 because these are the same. So p minus 1 is equal to kn. And so p is equal to kn plus 1. So every prime divisor of this is of the form kn plus 1. So that's pretty good. So now we're going to use this to show that there's infinitely many primes. So this is a pretty similar idea to like other ways to show that there's infinitely many primes. Just assume that there's finitely many primes of this form. Okay, interesting. And then let these be P1, P2, to Pm, where there's like m of these primes. Now, if we just times, we know that the n cyclotomic polynomial is like x to something plus x to something, or plus or minus x something plus or minus x something, and then plus or minus 1. So that means that like it's x times something plus or minus 1. And we know that this would not be divisible, like this would be like coprime to x, right? So x and x coprime. So this means that if p divided x, it would not divide this. So if we just set x equal to p1, p2, p3, p4, pm, then this thing would not be divisible by any of these primes. But you know that like there exists some p which divides this. And so because all the divisors of this are of the form kn plus 1, that means that there's some prime which was there's some other prime of the form kn plus 1. But then that would contradict the fact that these are all of the primes of that form. So there has to be infinitely many primes of the form kn plus 1. So are there any questions? Okay, I'll count down to 5. And then if you don't have any questions by then, I'll just move on. So 5, 4, 3, 2, 1. Okay. Let's move on to the next question. Wait, Haotian, how much time do you think we should give them for this question?
I think this problem deserves a hint and 5 minutes.
Okay. Wait, would you like to give the hint, or do you want me to give a hint?
Oh, you can give a hint. Actually, do you want to present the solution?
Oh yeah, I will.
Okay,
But
you can give a hint.
okay. So, notice that the left-hand side is equal to the 7th cyclotomic polynomial. So that means that if you consider a prime divisor of the left-hand side, if you consider a prime divisor of that side, the order of x with respect to that prime is 7. Wait, hold on. It's kind of hard to explain the hint in words, so I'll just write the hint down. Hint. Side is equal to 7 of x. P divides 7x over x to 7. Okay. Okay, I'll go over the solution now in case some of you guys really want to leave. Okay, so what we have is that either p equals 7 or 7 divides p minus 1, which means that p minus 1 is equal to it's like a multiple of 7 and p is equal to 1 plus 7k. But what this means is that like p is either equal to 7 or 1 plus a multiple of 7. So p is congruent to either 0 or 1 mod 7. Now, if you just think about some number which divides this, if p so like all the prime divisors of this are either 0 or 1 mod 7. So this is like mod 7, this is equal to like it's either equal to 0 times 1 times 1, like some number of times, or it's equal to 1 times 1 times 1 some number of times. So all divisors of are 0 or 1 mod 7. Now this fact is what we're going to use to finish off the problem, because we have that 2 y to the 5 minus 1. You can factorize this to be y minus 1. Y to the 4 plus y to the 3 plus y to the 2 plus y plus 1. Now, we know that y minus 1 is either equal to 0 or 1 mod 7. So y is equal to 1 or 2 mod 7. So let's try case 1, y is equal to 1 mod 7. Then we also know that this second part has to be either equal to 0 or 1 mod 7. So let's just find what that part is equal to. y4 plus y3 plus y2 plus y plus 1 is equal to 1 plus 1 plus 1 plus 1 plus 1 equal to 5 mod 7. That is not one of these. So it can't be this case. So now let's try this case where y is equivalent to 2 mod 7. Now y4 plus y3 plus y2 plus y plus 1. This is equal to 1 plus 2 plus 4 plus 8 plus 16. And then wait, 10 plus, I think this is equal to 31. But if I'm wrong, please correct me because I'm not very good at arithmetics. And so this is, what is this mod 7? I think it's 4 mod 7. But oh, look at this. 4, that is not 0 or 1. So that means that this case also doesn't work. But neither of our two cases could possibly work. So that means that there just aren't any solutions. So yep, that's it. So if you guys have any any questions, please feel free to ask now. But otherwise, if you don't have any questions, that's okay. Also, if you thought this question was hard, that's understandable because this was, I think, IMO shortlist N5 from 2000 something. I don't know. So it's supposed to be quite a tricky problem. Okay, it doesn't seem like you guys have any questions. So, hold on. Why is it, wait. Yep. So that should be the end of this. If you guys have any, if you guys want to talk to us about anything, you can feel free to stay behind. But otherwise, you guys are free to leave.
Hi, Danny.